In this video, we're going to take a look at section 3.4, which is on application problems, which is another way of saying word problems. So we're going to be looking at quite a few word problems in this section. And there's really no priming here. We're just going to jump right into the examples and talk about the different types of problems that you will come across in your homework. So let's take a look at this example. 1 canned juice drink is 15% orange juice. Another is 10% orange juice. How many liters of each should be mixed together in order to get 5 liters, that is 14% orange juice? So for many of these problems, there's going to be a couple of things you're going to be dealing with. And to organize all that information, it might be helpful to make a table. So how do I want to start this here? So there is a formula you can use to help you get a handle on this problem. And there might be different ways of describing it, but this is the way I have seen it in the past, which is Q equals A times R. A is the amount of whatever it is that you're working with, in this case juice. How much juice do you have? R is the percent of an ingredient in that amount. In this case, the ingredient we're looking at is orange juice. Q is the quantity, which, if you think about it, is synonymous with amount, but we're using a different word here to distinguish it from A. Q is the quantity of the ingredient in the overall thing that you're looking at. So it's the quantity of the ingredient in the juice. So in this case, Q would be the amount of orange juice in the juice drink altogether, right? And it's not a percent. Q is an amount. It's a number of liters. So if you have, for example, 5 liters of juice, how many liters of that would be orange juice versus whatever else is in the drink? All right. Now the problem is this formula applies to 3 different things in this problem. It applies to the first canned juice drink, which is 15% orange juice. It applies to another one, which is 10% orange juice, and then it applies to the 2 being mixed together. So it applies to 3 different things. So we're going to make a table to organize all that information. Right? And we'll make a row for each thing that the formula applies to. So we have the first juice drink, the second juice drink, and then the 2 juice drinks mixed together. We want to find the things from the formula for each of these, so we'll make a column for each thing in the formula. So we have A, we have R, and we have Q. And then we'll try to fill in the information based on what's given in the problem. So 1 canned juice drink is 15% orange juice. That's the R for the first drink. It's 15%, and we will write that in decimal form. Anytime you plug a percent into a formula, almost any time, you want to have it in decimal form. The second juice drink is 10% orange juice, so we'll put that here, 0.10. How many liters of each should be mixed together in order to get 5 liters? That's the amount for the mixture. We want 5 liters altogether. That's 14% orange juice. All right, so that'd be 0.14. So that's all the information we're given in the problem. Any box that's left open is technically an unknown value. There's one open box here that isn't actually unknown. This box here we do know. We have all the numbers we need to calculate that. But we will get to that in just a minute. You never want to put your variable on the right-hand side if you can help it. There are definitely situations where that has to be done. We will see some of that later in the course. But for this section, whenever you're going to set your variable, it should be in the first 2 columns, not in the last column. So I'm going to let X represent the amount of the first juice drink that I need to use. And since we've talked about system of equations in chapter 3, this would be a good time to make use of that. We will just let Y represent the amount of the second juice drink. So just use a second variable to represent this other unknown value. But the trade-off there is if you're going to use 2 variables in your problem to set it up, you have to come up with 2 equations in order to get a solution. And we'll get to that in just a minute. The next thing we're going to do is apply the formula. A times R is equal to Q. So for each row, the A times the R in that row gives us the result for Q, so we want to write it in the box for Q. So for the first row, for the first juice drink, we have a, which is x, times r, which is 0.15. Right. I don't know how that happened. All right. So we're going to multiply those together according to the formula. The formula tells me that's what q is equal to, so we write the result in the box for q. It'll be x times 0.15, which we'll write as 0.15x. So you know, typically when you have a variable times a number, you put the number in front of the variable. Same thing's going to happen in the second row. For the second juice drink, we'll multiply these together. A times r, write that result in the box for q. So we'll have y times 0.10, which gives me 0.10y. And for the mixture, we'll multiply these together, and this time it's not unknown, right? We have all the numbers here, and so we actually can multiply these together, 5 times 0.14, and I get 0.70. I like to put the 0 on the end. It's not necessary, but you can just put 0.7 if you want. All right, and so we've completely filled in the table. Now we need to extract some equations out of this information. And the two equations that we're going to get are from the amount column and from the quantity column. So think about the amount column here. We have X liters of the first juice drink, Y liters of the second juice drink, and then 5 liters of the two combined together. So if we take the amount of the first juice drink plus the amount of the second juice drink, it should add up to the amount of the mixture of the two being combined together. And so that'll be one equation. We have X plus y equals 5. And for these mixture problems, that's always going to be one of your equations. The other equation that will always be your second equation is the quantity. And it works the same way. This is the quantity of orange juice in the first juice drink. This is the quantity of orange juice in the second juice drink. This is the quantity of orange juice in the mixture of the two. So if I add these two together, the individual drinks, it should add up to the amount of orange juice in the two mixed together, right? And so we'll get 0.15x plus 0.10y equals 0.70. And there's my second equation. Now that I have two equations, I can solve this as a system of equations, just like we practiced in the previous few sections. And so we have a couple methods at our disposal. And I think the easier method to use here would be the substitution method, because it's pretty easy to solve this top equation for one of the variables. So I'm going to solve that for y by subtracting x to the other side, and I'll get y equals 5 minus x. I'm going to have to slow down here a little bit because I can tell the software is starting to lag a little bit because I've already done a lot of writing on the screen. So we solve the top equation for y, or you could solve it for x, doesn't matter which variable, whichever one's easier. And then we plug that into the other equation. So I'll plug this into the bottom equation. So I'm going to have 0.15x plus 0.10. In place of y, I'm plugging in 5 minus x. And then equals 0.70. All right, let's try that again. 0.70. Okay. And now we'll solve this equation for x. We'll start by distributing the 0.10 into the parentheses. So I'll get 0.15x. Okay, I'm going to try something real quick. I had this idea previously. If I skip to a different screen and come back, maybe it won't lag as much. So let me try to do that. So I'm going to jump ahead, because I think what it does is it kind of locks in all those different elements into one big element. So hopefully the lag will stop. Because I think what happens when I do a lot of writing is it's keeping track of all these little marks and it starts to slow down. But if I go to a different page and I come back, I think it kind of lumps them all together at that point. So let's see if my theory is correct here. So we'll distribute the 0.10, and that's going to give me plus I should put it like this, 0.5. Nope, I was wrong. It's still lagging. All right, 0.50. I like to put the extra 0 there. Minus 0.10x equals 0.70. All right, so we distribute the 0.10. We get this. Sorry about that stray decimal mark there. It's not supposed to be there. It's just 0.50. And this should have a decimal right here. We don't want to forget that. All right. I guess that's what this was supposed to be right here. All right. So we combine like terms. We could do a couple things at once here. we can combine like terms. And so those combine together to give me 0.05. The leading zero isn't really mathematically necessary, but I've heard from some people that makes it easier to read the number. But my habit has been not to put the leading zero there, so I'm trying to work on that. X, right, when we combine those two together. And this I'll subtract to the other side. So we're going to subtract 0.50 to the other side. So we'll do two things at once there to kind of speed things up a little bit. And so we're going to get equals 0.20. All right. Then solve for x. We divide by, do the leading zero again, 0.05. Divide that to the other side, 0.05. Use a calculator to compute the value for x, which will be 0.2 divided by 0.05. And we get 4. All right, so we get x is equal to 4. I don't know what it's doing. Oh gosh, okay, now it's just stopped writing completely. All right, so we get x is equal to 4, which, remember what x is representing. It's the amount of the first juice drink, which is the 15% one, which is what the first question is asking here. How many liters of the 15% orange juice should be in the mixture? We just found that out. That's what x is equal to. That's 4. After we answer that, it's going to ask us how many liters of the 10% one should we use. And so we want to be ready to answer that. And to find that, we need to know what y is equal to. And just like what we always do for a system of equations, once you find one of the variables, you plug it back into one of the original equations to find the value of the other variable. So I'm going to plug it in here, and I'll get y is equal to 5 minus 4, right? Because x is equal to 4. Let's try that again. And so y is equal to 1. And I apologize, it's really going slow here. All right, so we get y is equal to 1. And that's how many liters of the 10% orange juice. Sorry, it's not orange juice. That's how many liters of the 10% juice drink that we should be using to get a mixture that's 5 liters altogether and 14% orange juice. Okay, so that's a mixture problem. That's one kind of problem you will encounter on your homework. The next one we're going to look at here is an investment problem. So we have $6,300 invested, part of it at 10% and part of it at 9%. For a certain year, the total yield is $598. How much was invested at each rate? So for the investment problem, there's another formula you can use to guide you. And it's pretty similar to the formula we just used, actually. It's I equals P times R. And the letters mean something different, but the structure of the formula is really similar. P is the principal. It's the amount that you have invested. The total amount you have invested in that particular investment. R is the interest rate, which will be given as a percent, like we see up here. And I is the interest, which is a dollar amount. So interest rate and interest both sound pretty similar. So keep in mind, the difference there is interest rate is a percent. Interest is a dollar amount. It's the actual amount of money that you make on your investment. A table can be pretty useful in this situation as well. And so we'll make a table, but this time we only need 2 rows instead of 3 rows. So the formula really only applies to 2 things. It applies to our first investment, it applies to our second investment. And we'll need a column for P, a column for R, and a column for I. All right, so the first investment, the interest rate is 10%. Let's pick a different color here. 0.10. Again, I should put the leading zero there, like I was talking about in the last problem. The second investment, the interest rate is 9%, so we're going to write that as 0.09. For a certain year, the total yield was $598. That's the total interest. So I know they're using a different word there, but that's the total interest. So that's not the interest from any one investment. It's the interest from both investments together. So keep that in mind. So 598 doesn't get plugged into either box here. It's what both of these boxes would add up to, is what they have to equal together. And so we don't know anything else on this table, so we're going to have to start using a variable. I will let, or two variables, as the case may be. I'll let X represent the amount invested in the first investment. I'll let Y represent the amount invested in the second investment. Then we use the formula to fill in the last column. We multiply the first two things together, write the result in the box for the third column, because the formula tells us that that's where it belongs, right? P times R is equal to I. This is P, this is R. If I multiply those together, it equals I, so I write the result in the box for I. It'll be 0.10x, and when I multiply these together, I'll get 0.09y. Because I'm using two variables, I will need to have two equations. One of my equations I think is pretty obvious right here, which is this one. If I take the interest from the first investment plus the interest from the second investment, it should add up to the total interest, which is $598. So I'll have 0.10x plus 0.09y, and that should add up to 598. The other equation is given by this. There's $6,300 invested altogether. So if I take the amount invested in the first investment, which is X, plus the amount invested in the second investment, which is Y, that should add up to the total amount invested, which is $6,300. So I don't really have it in the table, but I guess I could have put it like this, right? The amount invested altogether is $6,300. So we get a system of equations pretty similar to our last example, and I think we should just solve it in a very similar way. We'll use the substitution method. So I'll subtract X to the other side. I get Y is equal to 6,300 minus X. I'm going to plug that into the bottom equation for Y. So I'll get 0.10x plus 0.09. In place of Y, I'm going to plug in 6,300 minus X equals 598. I'm sorry, this should have been a better zero here. All right. And then we're going to solve that for X. We will start by distributing the 0.09 into the parentheses. So I'll continue up here, even though I'm really running out of room. So let's see if it'll fit. We get 0.10x plus, let's do this in our calculator, 0.09 times 6,300 be 567 minus 0.09x. Oh goodness, okay. Okay, there's x, okay, equals 598. And just like we've been doing the last couple of examples where this has happened, we're combining like terms here, not adding this over to this because they're already on the same side of the equation. We just combine them together. We'll get 0.01 this time, x, and while we're at it, subtract the 567 to the other side. And so we'll get 0.01x equals 31. Now we will divide by 0.01 on both sides. So divide by 0.01 and we get 3,100. So I'll use a different color. So we get, excuse me, x equals 3,100. Excuse me. So remember what x represents. It is the amount invested at the 10% investment, at the 10% rate, which is what the first question is asking. How much was invested at 10%? We're going to type in 3,100 into this box. However, it will ask us the next question, which is how much was invested at 9%. So we still need to know that. And we can find that out by taking our answer for x, plugging it back into one of the original equations. I think this would be the best one. And then solving that for y to find out what y is equal to. So we'll have 6,300 minus 3,100, which gives me y equals 3,200. And so that's how much was invested at 9%. All right, so that was an investment problem. Let's take a look at the next example. A plane flying the 3,458 miles from New York City to London has a 70 mile per hour tailwind. The flight's point of no return is the point at which the flight time required to return to New York is the same as the time required to continue to London. If the plane's speed in still air is 900 miles per hour, how far is New York from the point of no return? Okay, so this problem is a distance problem, a distance, rate, and time problem. The more technical term for it is uniform motion. This is a uniform motion problem. The formula for that is d equals rt. R is the speed, it's the rate of motion, that's what R stands for, rate of motion. This time R is not a percent, it's a mile per hour, or kilometers per hour, whatever units you want to use. T is the time, and D is the distance. So this formula is probably the one we're most familiar with in our day-to-day lives, because anytime you've done any kind of traveling, for example, on a highway or something, this formula has governed your trip. How fast you're driving on the highway, if you're going 70 miles per hour, dictates how long it's going to take you to get where you're going, and that's something you want to keep track of because you want to know how long the drive is going to take, right? So if you have 350 miles to travel, and you can go 70 miles per hour most of the way, that's going to take you about 5 hours. And that formula, the way you figure that out mathematically, this is what this formula does, right? 70 miles per hour, 350 miles, you divide it over here to find the time, and you get t is equal to 5, right? So that's how that formula works. However, in this situation, we have a couple things going on that we have to keep track of. So we have a plane that's flying from New York to London. So I like to draw a picture for these problems. And you don't have to get a map and draw the United States and draw England and find where these cities are. Just think of it as a straight line. This is New York City, and over here is London. All right, and so the plane is flying from New York City to London. So try to think of it as trying to draw a straight line, but think of it as a straight line. And it has a 70 mile per hour tailwind. So I'm not, now that I'm thinking about it, I'm not 100% sure what a tailwind is. I don't know if I need to pause the video and look that up real quick. It's got to be, there's one of two things. It's either a boost to the plane, that it's a wind that's blowing from behind the plane, pushing it towards its destination. Or it could be a wind that is blowing against you, slowing you down, pushing you backwards in the direction that you came from. I think that's called a headwind. So when you're flying into a headwind, it's when the wind's pushing back against you. So I'm pretty sure a tailwind is you're getting a boost. The wind is blowing you in the direction of your destination, right? So we have this plane. So we have the wind. Let's go ahead and mark the wind here. The wind is blowing in this direction at 70 miles per hour. All right. And so the plane has its own speed, right? So the plane is able to travel at a certain speed on its own. In fact, it tells us right here, the plane's speed in still air is 900 miles per hour. So with the 70 mile per hour tailwind, it's going to be going 970 miles per hour. Excuse me, I put the wrong number first. All right, so 900 miles per hour on its own, plus a boost of 70 miles per hour from the wind, means going towards London from New York, the plane will have a total speed of 970 miles per hour. Right. However, if it changed its mind and wanted to return back to New York, so this is what the question's about, is if it wanted to stop going to London and wanted to turn back around and go to New York, it would be flying into the wind and would be slowed down by 70 miles per hour. So if it turned around and went this direction, the plane would only be going 830 miles per hour, right? Because on its own, it would be 900 miles per hour minus that 70 mile per hour wind means the plane would only be able to go 830 miles returning to New York. So we have a different speed depending on which direction we're moving in. If we're heading toward London, the speed is 970. If we're heading back to New York, the speed is 830. All right, and we want to find the point of no return where, so it's some distance right here. I wouldn't put it exactly in the middle because I don't think it's going to be exactly in the middle, where the time it would take to continue to London would be the same as if it decided to return back to New York, right? So the time in either direction here is going to be the same. So we're looking for what that distance is where the time to go back is the same as just going forward onto your your original destination. All right. So we're going to make a table, and we'll need 2 rows because this formula applies to 2 different things. It applies to heading towards London, because there's one speed if you're heading towards London, and it applies to returning back to New York City, because there's a different speed if you're heading back to New York City. And when the speed changes, the formula has to be reapplied, right? So we're going to look for the things that are in the formula, which is R, T, and D. Right? And what we know is that if we're going toward London, the speed is 970 miles per hour. If we're heading back to New York, the speed is 830 miles per hour. I'm sorry, I don't know why I'm misspeaking so badly. At this point of no return that we're talking about, the whole definition of it is the time required to return to New York is the same as the time required to continue to London. So here we don't need to use 2 different variables, x and y, because it's the same time. So at this point of no return, which is what we're looking at in this table, the time to fly onwards towards London would be x hours. The time it would take to fly back to New York would be the same. However many hours it would take to get to London, it's going to be the same number of hours to return to New York. That's what the point of no return is. That's its definition. So we will use the same variable to represent both of those. That's the only time you are allowed to use the same variable for 2 different things, is if you know they're equal to each other, which is what we're being told here. The times will be the same. Right? And so now we can use the formula to fill in the rest of the table. Right? We take R times T for the first row, and that'll give me the distance. The distance it would be to continue forward from here on to London. So we're talking about this distance here. It'd be 970x, right? The bottom row, if I multiply these together, R times T, the formula tells me that's equal to your distance, so we'll write that in the box for distance. That represents the distance if we wanted to head back to New York. So if we decided to turn around, what would that distance be? That's what that expression represents. And what we know about these distances, if you look at this diagram here, we have this part of the trip would be 830x. That's the distance for that part of the trip. The distance for this part of the trip would be 970x. And we know the total distance between the 2 cities is 3,458. So it might have been a little detail you overlooked, but it was at the very beginning. So the equation here is if I take this distance, which is the 830x, and this distance, which is the 970x, together it should add up to the total distance, which is 3,458. 3,458. Right. All right. And so that's my equation. And I only need one equation this time because I only used one variable. So we have 970x plus 830x, and that equals 3,458. And I'm sorry about this. This is kind of bugging me, but I don't think I can fix it. I guess I can just rewrite it. So it'd be 830. It's not going to let me rewrite it either. How many marks did I make there? 830x. That's this distance right here. Okay. And so we'll solve this equation. We'll just start by combining these together. So we have 970 plus 830, and that's going to be 1,800. So I have 1,800x equals 3,458. We divide by 1,800 to solve for x. And I'm sorry, I'm going kind of slow here, but I want to make sure it'll write for me because it's getting laggy again. Thankfully, it's not a system of equations, so once we get the answer, we're done. I get x equals 1.0 9, 2, and then 1, 1, 1's repeating. So x, remember, is the time that it would take to continue to London or to return to New York. It's the same time either way. And it's going to be 1.921 hours, right? But that's not what the question's asking me. It's not asking me how many hours would it be to get back to New York or to go on to London. It's asking me what would the distance be from New York. So based on where we currently are, this point of no return, what's the distance back to New York? That's the 830x, right? This thing represents the distance from the point of no return back to New York City. So we want to take what we found for x, plug it back into this box to unlock that piece of information so that we can know the distance, because that's what the question's asking us. So it's going to be 830 times x, which is this 1.92, sorry, it's not writing for me, 1.92111 repeating, which I still have in my calculator, so I'm just going to leave it in my calculator and take the number of my calculator times 830, and I get this answer, 1,594.52222, just 2's repeating. All right, let's try that one more time. All right. 2's repeating. All right. And the problem says round to the nearest integer. So that means just round it to the nearest whole number, which will be, because that's a 5, we'll round that up. So it'll be 1595. If I can get it to right. Okay. So I'm sorry about that. I might need to switch to a new software. I mean, this works pretty good. It's free. It's an open source software. That's why I used it. But I've been having this problem where if I've done too much writing on the screen, it really starts to get laggy. So for especially lengthier examples like we're doing here, I might need to use a different software that can handle a little bit more work. So, all right, so that's what you would type into Math Excel. Let's take a look at another example. So I apologize for how it's behaving. So I know it might be frustrating to have to watch. Okay, we have two motorcycles that are traveling toward each other from cities that are about 425 kilometers apart at rates of 100 kilometers per hour and 70 kilometers per hour. So if the kilometers per hour is bothering you, just think of it as miles per hour. The units really don't make a difference to the math that we're going to be doing. So think of it as 100 miles per hour if that helps. They started at the same time. In how many hours will they meet? So this might seem like a completely different problem. It's another distance problem, so we're going to use the same formula here, d equals rt. All right, I'm going to draw another picture. We have two motorcycles traveling toward each other from different cities. I'm just going to think of it as a straight line. So here's one city, here's another city. Let's try all that again. I don't know, I'm not liking how that's looking here. So let's try it again. This is one city, and we're traveling toward another city. That looks better. All right. Okay, and we're told these are 425 kilometers apart. So that's the distance between them. The first person on their motorcycle is going 100 miles per hour or kilometers per hour, or whatever you want to call it. The second person is going 70. That's their speed. Right? They start at the same time. And how many hours will they meet? Now, they won't meet exactly halfway in the middle because this person's going faster. He or she is going to get further along before they actually meet with one another. So at some point, let's say this is where they meet right here. Right? So they're going to meet somewhere in the middle, not exactly halfway because the speeds are different. Right? This is where they're going to end up meeting at. And we want to know how long will it take for that to happen. So I'm not asking for the distance that they're traveling. I'm just saying for the time. How long is it going to take until they meet one another? All right, so we're going to draw a table. All right, and we'll need two rows again, just like we had before. We are making two rows because there are two motorcyclists. Let's try that again. All right, and then we'll make a column. I didn't leave myself a lot of room here, so I hope I can fit everything. Column for each variable in the formula. we'll fill in what we know. We know the speed of the first motorcyclist is 100 kilometers an hour. The speed of the second motorcyclist is 70. We don't know the time, but we are told that they start at the same time. That means they'll travel for the same amount of time because they're starting at the same time, and when they meet, they'll end at the same time. So we don't know how long that is, but we'll just call it X for the first motorcyclist. And because they're traveling for the same amount of time, the time for the second motorcyclist will be the same. It'll also be X. So again, in this situation, we don't need two different variables because the unknown value for both of them is the same, so we can use the same variable to represent both of them. And then we'll use the formula to multiply across, so we get 100 times X. That represents the distance traveled by the first motorcyclist. For the second motorcyclist, we multiply across, we get 70 times X. And again, that represents the distance for the second motorcyclist. So 70x represents that person's distance. And they are 425 kilometers apart. So it's really similar to the problem we just did. If I take the distance of the first motorcyclist and the distance of the second motorcyclist together, it should add up to 425. Right? So I'll have 100x, that's the distance traveled by the first person, plus 70x, which is the distance traveled by the second person. Together, the total distance they will travel is the 425 kilometers because that's the distance that they were apart. So together, they've covered that entire distance that they were separated by to begin with. All right, and so we're going to solve this for x. We'll start by combining these together. So we get 170x equals 425. And then to solve for x, we divide by 170 on both sides. And we get x is equal to, I'll use my calculator for this, 425 divided by 170. And we get not the nicest answer, but not the most terrible answer. We get 2.5. And that's hours, right? Because x is representing the time. And that's exactly what we're looking for. So this time we don't have to figure out the distance. The time is the answer that we're looking for. And so we're done. 2.5 hours is how long it'll take for them to meet. All right, got a few more problems here, so I'm sorry this video is going to take a little longer than the other ones, but I think we got most of the worst problems out of the way. So let's take a look at this one. A student makes a $10.50 purchase at the bookstore with a $20 bill. The store has no bills and gives the change in quarters and 50-cent pieces. There are 30 coins in all. How many of each kind are there? All right, so we have quarters and we have 50-cent pieces. We can let x represent the quarters and let y represent the 50-cent pieces. And what we don't need a table here for this. We just need two equations. Right? And so we'll let x represent the quarters and y represent the 50-cent pieces. And so we will need two equations because there are two variables here. There are 30 coins in all. And so we'll have x plus y equals 30. And we know the value of the coins. It's not $10.50. We have to be careful here. The change this person is getting, they're paying with a $20 bill. The cost of their purchase is $10.50. And so if you subtract, the change they should be getting is $9.50. And that's the change they're getting in the quarters and 50-cent pieces. And we talked about this earlier in the video, but sometimes I'll get students doing it here as well. They'll say, okay, well, x plus y equals $9.56. I don't know why I said 56 cents. That's weird. The change they're getting is $9.50. So they'll say x plus y is $9.50. But that isn't correct. This equation is not correct. I think we did it in this video. I might have said this in the last video. I can't remember where I mentioned it. Because here x is representing the number of quarters, which is what it should represent. It should represent the value of a quarter because we know the value of a quarter. It's 25 cents. But here we're using it as the value of the quarters altogether, which isn't the way we're using it up here. So we're going to let x represent the number of quarters, and y represents the number of 50-cent pieces. So this equation still makes sense. The number of quarters plus the number of 50-cent pieces adds up to the total number of coins, which is 30. Here the equation doesn't make sense anymore. the number of quarters plus the number of 50-cent pieces doesn't add up to the value of the coins, $9.50. To get the value of the coins, we have to multiply by the value of each coin. And so we take the number of quarters times the value of each quarter, which is 25 cents, and that gives me the total value of the quarters. And then here, the number of 50-cent pieces times the value of each 50-cent piece, which is 50 cents. And that gives me the total value of the 50-cent pieces, and that together has to add up to the total value of the coins, which is $9.50, which is the amount of change that this student was due. All right, and so that's how we get our second equation. All right, so now we want to solve this system of equations, and I think substitution method, again, is the best way to go here. We just subtract x to the other side. We get y is equal to 30 minus x. We'll plug that into the bottom equation, so we get 0.25x plus 0.50 times y, which is 30 minus x, and that equals $9.50. All right, so we're replacing the y variable here with 30 minus x. And then we solve this equation for x. We'll distribute the 0.5, so we get 0.25x plus, this will be 15, minus 0.50x equals $9.50. And we found ourselves in this situation multiple times. We'll combine these like terms together. We get negative 0.25x when we do that, and then subtract the 15 to the other side. And so we're going to get, I should be able to do this in my head, it'll be negative $5.50. Now we can solve for x by dividing the negative 0.25 to the other side, and we have to get a nice answer here for this word problem to make sense. We can't get a negative answer, and we can't get a decimal answer. It has to be a positive whole number, or otherwise something went wrong. So I have 5.50 divided by 0.25, and we get 22. So thankfully it worked out nice. We have 22 quarters, right? So how many quarters are there in the change? 22, because x, again, remember, was representing the number of quarters. To get the number of 50-cent pieces, we'll take x equals 22, plug it back into one of the original equations, solve for y. So we'll get 30 minus 22, which gives me 8. And so that'll be the number of 50-cent pieces. So there'll be 22 quarters and 8 50-cent pieces. Whoops. Okay, I'm going too fast here, I guess. So, all right. So that is how that problem goes. Let's take a look at the next example. Alvin paddled for 4 hours with a 3 kilometer per hour, again, if that kilometer bothers you, just think of it as miles per hour, 3 kilometer per hour current to reach a campsite. The return trip against the same current took 7 hours. Find the speed of the boat in still water. All right. So we're paddling up a river or down a river. So here's the river right here. And let's say the current is moving in this direction. All right, so this is the current. These arrows represent the current here. And that current is 3 kilometers per hour. All right. So Alvin's boat is somewhere in the river. And to go to the campsite, paddling with the current, it took 4 hours. So let's say starting from here and getting here took 4 hours going with the current. So maybe I should put it over here instead. So this is where Alvin starts. He goes down the river with the current. This is where his campsite is. This is a 4-hour trip going in that direction. All right. Going against the current, leaving the campsite, going back where he was parked, takes 7 hours. Going against the current. All right, so this is another distance, rate, and time problem. And a table will definitely be useful here. And we need 2 rows again. Let me try that again. 2 rows. All right, and we need a column for each variable in the formula. So this is to the campsite. This is from the campsite. RT is equal to D. So we build the formula into the table. Okay, let's fill in what we know from the problem, so we know the time. So this time we're given the time. So the last couple of problems we didn't know the time. This time they're telling us what the time is, and what we don't know is the speed. So to go to the campsite, the trip took 4 hours. To go away from the campsite back to where he was parked, the trip took 7 hours. What we don't know is the speed, but we have a little bit of detail about it, right? We know there's a current affecting that speed. We're trying to find the speed of the boat in still water. That's the thing we don't know, so we're going to call that x. And when going to the campsite, Alvin will be able to paddle his boat at that speed, plus get a 3 mile per hour or 3 kilometer per hour boost from the current. So Alvin's total speed will be x plus 3. However fast he's able to paddle the boat on his own, plus an additional 3 kilometers per hour from the current. Going away from the campsite back to where he was parked, Alvin is able to paddle the boat at x miles per hour, but will be slowed down by the current by 3 kilometers per hour. So Alvin's total speed will be x minus 3. All right, and so that's how we'll fill in that column. And then now that we have the first 2 columns filled in, we can use the formula, multiply the r and the t together to get the distance. And so we'll do that. And I didn't leave myself enough room here, so it's going to kind of spill out from the table. We'll have x plus 3 times 4 to give me the distance to the campsite. So I'll put the 4 first times the x plus 3 in parentheses. And then from the campsite, we're going to have 7 times x minus 3. All right. And what do we know about these distances? This is the distance to the campsite. This is this distance here. It's 4 times x plus 3. And this is the distance from the campsite back to where he started, right? So it's going to be this distance here. This will be 7 times x minus 3. What do we know about those two distances? They are the same. The distances are equal to each other. And so to get our equation, we're going to set these equal. We'll have 4 times x plus 3 equals 7 times x minus 3. And that's going to be our equation. So we'll distribute the 4. And we'll get 4x plus 12 equals 7x minus 21. We will subtract the 4x to the other side. I'm going to bring the x to the right-hand side to keep it positive. And then while I'm at it, I might as well add the 21 back to the left-hand side. And so we're going to get 33 here. 33, not x. Why am I putting x there? We'll get 33 equals 3x. Now I can solve that for x by dividing 3 from both sides. And I get x is equal to 11, which is the answer we're looking for, right? Find the speed of the boat in still water. That is x. That is the answer we're looking for. So there's nothing else I need to do. The answer is 11 kilometers per hour is how fast Alvin is able to paddle the boat on his own. Okay, so I have a couple more examples left. I know we're reaching the 50-minute mark, so I apologize for the length of the video. These last 2 examples, however, are in the lecture for my students to practice. Like when I'm teaching this in class, if we have time, we get to these last couple of examples and I let my students in class do them, since I've already done a problem similar to what you're about to see. So I think that'd be a good idea for you guys to try. So if you're watching this video, go ahead and pause the video. See if you can figure this problem out. See how far you can get with it. Do as much as you can. And then resume the video to see if you are on the right track or if you got the right answer. So soybean meal is 12% protein. Cornmeal is 6% protein. How many pounds of each should be mixed together in order to get 240-pound mixture? That is 7% protein. All right. So it's a mixture problem. This is like the first example that we did at the beginning of this lesson. And the formula we talked about for that was Q equals A times R. And so we'll make a table, and whenever you have a mixture problem, you need to have 3 rows for that. So we'll have 1, 2, and 3 rows, right? And so we have the soybean mixture. I'm just going to put soy here. With the cornmeal, I'm just going to put corn. And then we have the 2 mixed together. Right. And so what we're looking for each of these is the things from the formula. We're looking for A, we're looking for R, and we're looking for Q. And we'll get Q by calculating it. So really what we're looking for is A and R. Once we get all of that information for all of the things involved, the formula helps us figure out what Q is equal to. So for the soybean meal, it's 12% protein. So we will put 12% for the soybean meal. For the corn meal, it's 6% protein. And for the mixture of the two that I'm creating, I want it to be 7% protein. We know the mixture is supposed to be 240 pounds. And so that's the amount of the mixture. What we don't know is how much of each ingredient, how much of each thing we're supposed to use to get that 240-pound mixture. So these are going to be unknown. So I'm going to use a variable to represent them. I'll let X represent the amount of the soybean meal that we need. And I'll let Y represent the amount of cornmeal that we need. Now that we have the first two columns filled in, we use the formula to fill in the last column. So we just multiply across. We'll have X times 0.12, that gives me 0.12X. We'll have Y times 0.06, which gives me 0.06Y. Sorry, I feel a little bit out of it today. I apologize. I keep making mistakes. And then we'll have 240 times 0.07, which will be 16.8. All right. And so that tells me of the 240 pounds of the mixture, 16.8 pounds of it is just protein. And there's going to be some amount of, pounds of other stuff, but there's exactly 16.8 pounds of protein in that 240 pound mixture. All right. So because we use two variables, we need two equations. And we talked about this with the first example that we did. The first equation will be from the amounts. The amount of soybean plus the amount of cornmeal has to equal the total amount of the two mixed together, which will be 240. So we'll have X plus Y equals 240. For the second equation, it's from the quantity. The quantity of protein in the soybean meal plus the quantity of protein in the cornmeal should equal the total amount of protein in the two mixed together. So I'll have 0.12X plus 0.06Y equals 16.8. And now we have a system of equations to solve, which we will do the same way we've done all of them so far with all of these word problems. We will use substitution. So we'll solve this for Y. We get this. And then we'll plug that into the second equation. So we get 0.12X plus 0.06Y, which is 240 minus X, equals 16.8. Then we solve this for X, so we get 0.12X plus, we'll have 0.06 times 240, which is 14.4, minus 0.06X equals 16.8. We'll combine our like terms, so we get 0.06X, supposed to be a 6 there, and we'll subtract the 14.4 to the other side if it'll let me. Okay, now it's giving me a hard time. All right, 14.4, subtract that to the other side, and we'll get 0.06X is equal to 2.4. Oh goodness, okay, let's try that again. 2.4, all right. Then we solve that for X by dividing the 0.06 to the other side, and we'll get X, try to get X here, equals, this will be 4, pretty sure. All right, yeah, it's going to be 40, excuse me, not 4, it'll be 40. Let me just double check. All right, so we'll divide by 0.06, yeah, 40. All right, and so X is equal to 40. So that tells me the amount of the soybean that we want to use. Now, careful here, because they did a switch on us. Even though they mentioned soybean first in the problem, in the question, it's asking for cornmeal first. So don't plug in 40 here, because that's asking for the amount of cornmeal. What we found first was the amount of soybean. So let's go ahead and find the amount of cornmeal by plugging this into one of the original equations and solving for Y. All right, so we have Y equals 240 minus X, which is 40, and I get that y is equal to 200. And so that's the amount of cornmeal. And that's what they're asking for first here, right? So y is the amount of cornmeal, which we found is 200. That's what you want to type into this box here. And then once you confirm that answer, then it will ask you for the amount of soybean meal, and that's where you will type in the 40. All right. Last example. All right. And again, I would recommend that you try this problem first by pausing the video, see what you can do with it, and then resume it to see if you were on the right track, if you got the right answer. So a non-toxic furniture polish can be made by combining vinegar and olive oil. The amount of oil should be 3 times the amount of vinegar. How much of each ingredient is needed in order to make 30 ounces of furniture polish? All right, so we don't need a table for this one. We're just going to set up a system of equations. We have 2 different ingredients that we are combining together. So it might seem like a mixture problem, but we don't have the percents. You know, it's not of this amount. We have this particular percent of an ingredient, and that you're mixing these multiple things together to get a new thing where you want a certain percent on it. So it's not like a mixture problem like we just did a moment ago. So this is a different kind of problem, and it doesn't need to be done in the same way. So we're combining vinegar and olive oil, and we're told the recipe for this, the amount of oil should be 3 times the amount of vinegar. So I will let X represent the amount of vinegar, let Y represent the amount of oil, and then I can make an equation out of this next sentence. The amount of oil, that's Y, should be, that's equals 3 times the amount of vinegar, which is X. So there's my equation. There's my first equation anyways. We have Y equals 3 times X. How much of each ingredient is needed in order to make 30 ounces of a furniture polish? Well, since that 30 ounces is completely composed of vinegar and olive oil, that means the vinegar and the olive oil have to add up to that 30 ounces, right? And so the amount of vinegar plus the amount of oil has to add up to 30 to give us a 30 ounces of furniture polish. All right, so that'll be my second equation. And we needed 2 because when you have 2 variables, you need 2 equations. This one is definitely most easily done by the substitution method. It's already solved for y, so I'm going to plug that into the bottom equation here, and we'll have x plus 3x equals 30. And then we're going to solve this for x by combining the x's together. We get 4x, and then dividing by 4 on both sides. And we'll get x is equal to 7.5. Now, the problem with what I just did, because if you're cooking or whatever, when you're doing ingredients, decimals are sometimes pretty handy to have. So 7.5 ounces would be a good way to describe that. But the directions here say type as mixed numbers if possible, otherwise integers or fractions. So it doesn't want a decimal answer, unfortunately. So instead of writing it as 7.5, which is what you would get from your calculator, reduce this fraction. You can reduce it by dividing a 2 from the top and bottom, and you'll get 15 over 2, which can be written as a mixed number by taking the 2, dividing it into the 15. It goes 7 times, and we get a remainder of 1. And so that remainder of 1 is still getting divided by the 2, so we get 7.5. So that's what they want you to write here. Right. 7.5, which, I don't know, maybe I made that more complicated than I needed to. Because you probably know 0.5 is 1/2, so you could have just taken the decimal and wrote that as 7.5. So whatever works for you is fine. So if you can convert it from decimal into fraction form, great. If not, you leave it as a fraction and convert it to mixed number by dividing. So that's the way you would do that. So that is what x is equal to. Now we need to find y, so we'll plug that in up here. And I don't know, mixed number is not the best way to do computations. So I would not plug in 7.5 for x. I think that'd be a hard way to do that computation. So either as a decimal or as an improper fraction. So if you want to do this as a fraction, maybe we could just leave it as 15 halves and plug it in up there. I'm kind of leaning towards, let's just do this as a decimal, and then we can convert the decimal into a mixed number from there, hopefully. So we'll plug in 7.5 here. We get y equals 3 times 7.5, which will be 22.5. Which, as I mentioned a moment ago, I don't know, I don't always see the most common sense way of doing things. The 0.5 is 1/2, right? So you can just write the 0.5 as a half. And that's how you write it as a mixed number, 22.5. All right, and so that's what you would type into this box right here. All right, so that concludes, finally, section 3.4, which is on word problems.